Assalamualaikum warahmatullahi wabarakatuh. Today, me, Nur Natasha binti Ramzan, and my group members Wan Aina Ashikin binti Wan Muhammad Aziman and Muhammad Aiman bin Nur Is Jamal Nasir will present about applying line integral in mass of spring and work done. Firstly, for the introduction, an integral in which a function is integrated along a curve in the coordinate system. It can be represented as either a scalar field or a vector field. It also can be integrate both scalar value and vector value function along a curve. Value obtained by adding up the values of each point on the vector field. To describe integral of function that follow curves, vector value function have the identical input and output dimension and are frequently modeled as vector fields.
Assalamualaikum, my name is Wan Aina binti Azman and I will proceed with some basic curve that need to know to do as well as limits on the parameter if required. For ellipse, x square over a square plus y square over b square equals to 1. For counterclockwise, we use x equals to a cos t, and for y we use b sin t. For clockwise, we use x equals to a cos t and then y equals to negative b sin t. For circle, which is x square plus y square equals to r square, for counterclockwise we use x equals to r cos t, and for y we use r sin t. For clockwise we use x equals to r cos t, and for y we use negative r sin t. For theorem 3, which is work done as a line integral, we use the formula of integrate f dot tr. Next, we continue with the application of line integral. For example, line integral can figure out how many calories a swimmer will expend when swimming a certain path, and then we can be used to compute the line mass of a wire. Last but not least, the surface area of the three-dimensional plane is calculated with a line integral.
For case study 1, a researcher did a study of a helical spring, especially in mechanical field that used for engine starters and hings. Imagine that you are a researcher. You were given a spring of circular helix in figure 1 to make a new model of toys. What is the mass of the spring that we'll use in the model? Use line integral to find the mass of a spring in the shape of circular helix. Vector of RT equal to cos t, sin t, and t. T more than equal 0 and t less than equal 6 pi. And the density of the spring is rho x y z equal to 1 plus z. Use grams for the unit.
So to solve the solution for the case study 1 manually, we have to find the density of the spring, which is the function of it. So from here we get to find the xyz for the spring. So we have to integrate them, and we have to find the dx dt that we get from it. We have to find it in here in the parametric equation. So after that we get the x, y, and z. We get the cos t, sin t, and t, which is where the 0 is over t and not matched to 6 pi, which is this is where we get to the step 3 for the calculate ds, which we had to find to determine the r prime t multiplied to dt. So after we square root that all the derivative of all the s, y, and z, and from that we had to solve it, and we got the prime 2 square root of 2 of dt, and from that we had to solve using the integral, which we get from here. We have 6 point and 0, which we had to integrate the 1 plus z, and then we had to put the ds. We can change the ds to the prime 2 we got from the step 3, and then we multiply them, simplify them. After that, we get the m of them is 277.89 gram. And also we can use the Maplesoft to find them, to find the really easy to find it, which is we have to first we have to restart to reset all the equation from before you use it, and then we have to put the simulation of the vector calculus and the plots for to see how the spring looks like, and then we have to put the code, the plot, and you can name it everything you want, and then we can change to look how it looks like. From there we get the plot that we also found it in the step 2, and after we get it, we can see the plot for the spring, how the 3D model looks like. And then from that we can get the r dt. From this, cos t, sin t, and plus t, which we get from the step 2, and we had to function it into the ds, which is where we get the prime 2 from the step 3. And then also we get the 1 plus z that we got from the case study of it, and we had to, at the same time, we combine it, and then we integrate it with 6 pi over 0, and we get the plus prime 2 pi of power of 2 plus 6 square root of 2 and pi.
Case study 2, a researcher did a study about movement of rugby ball that was played by rugby player in a game. As a student, you are required to find the work done that can be used by rugby player to throw the ball in goalposts. Assume that rugby ball moves in the force field F as is stated counterclockwise along the particle path 4x squared plus 9y squared equals to 36 at the interval 0 to 2 pi.
Also, we can find the same answer for the solution for the case study 2 by using the software we use, the Maplesoft. From here, we had to put the code for the wave vector calculus, which we cannot see from here, but we list all the calculus that we're gonna use in our plots, and this is the plots that we putting, and input the equation that we got from the step 3, and from that you can adjust how you want to clearly see how it looks, and from there we can see the plane itself in the box here, and there from there we can get the same answer for the step for the r prime, which is 3 cos t 2 sin t and plus 0. And from here we get to differentiate the dr for the step 4, and after that we combine them the same also with the step 4, and we multiply it with dr from the function for the dr and the f function, and from that we can get the integrate both of them, and we get the 12 pi from here. Same also with the solution for case study 2. For solution case study 2, we had to first find the function for s, y, z, which is, we can see from here, we got 2s minus y plus z for I, s minus z power of 2 for j, and 3y minus 2z for k. The second step is to determine the parametric equation for s, y, and z. The elite, we can see here we got the 4s power of 2 and 9y power of 2, which is equal to 36, and s power of 2 and y power of 2 we got equal 1, and so on with this. So we had to, from here we can see we had to discriminate them into the smallest, to simplify them into the smallest one, and from then we can see that we get the parametric equation for all of this, and also we gonna have to turn it into prime for differentiate them. So we can see s prime equals to negative 3 since t, y prime equal to 2 cos t, and z prime equal to 0. This next we have to multiply with both of them, which is the function and the r prime. So from here we can see the 3 cos from the parametric equation we get from up here, and then we have to go for the function. We get that for negative 3, and from there we have to multiply them, combine them into the r prime. From there we have the negative 3 sin t and the 2 cos t and 0, and then we have to multiply them, and we got the final. So equal, we have got the negative 8t cos t sin t plus c power of 2t and plus c cos power of 2t, decimation of time. And the final for the soft root done from here, we can get that from the rod scanner here, the f, the function of dr, we have to integrate them into from we get from the step 3, and then we had to finish the work, solve them, and we get the equal to 12 of the equation here.
As a conclusion, line integrals are widely used in a variety of fields, and the scalar field and vector field can be used to represent the integral function that needs to be integrated, and then a work done is represented by vector field. The last one is vector line integrals are applied to find the mass of a spring, and work done are calculated by using vector lines integral.